Welcome. Have you ever stopped to think about the invisible magic that connects our entire digital world? You know, how you can send an email from your desk and it just arrives on the other side of the planet? Well, it all runs on this incredible web of networks. So let's pull back the curtain and take a look at the digital highways that make it all happen.
Seriously, think about it. You're sitting at your desk in, let's say, Chicago. You click a link, and bam, you're grabbing data from a server in San Francisco, almost instantly. What is actually happening in that split second? That's the exact journey we're going to follow.
Here's how we'll do it. First, we'll start small, right there in your own office, with your local network. Then we're going to zoom out and see how whole offices get linked up across the globe. From there, we'll peel back yet another layer and look at the deep-down infrastructure that powers everything. And finally, we'll talk about why actually designing and documenting these networks is one of the most important jobs of all. Okay, first stop. We're starting in our immediate digital neighborhood. This is the network that you use every single day, probably without even thinking about it. We're talking about the local area network, or as you probably know it, the LAN. The easiest way to think of a LAN is like your building's own private, super fast intercom system. It's what connects all your computers, printers, and local servers together inside a single office or a school campus. And it is fast. We're talking speeds that let you move massive files around in seconds. And because it's owned and operated by the organization itself, all that local traffic stays local, zipping around efficiently. So how do you actually plug into this local network? Well, you've really got two main flavors. You've got your classic Ethernet cable, the wired connection. This is your go-to when you need absolute rock-solid reliability and the fastest speeds possible. And then, of course, there's Wi-Fi, giving you that wonderful freedom to take your laptop to a conference room without being tethered to the wall. It's the ultimate trade-off, really. Do you want maximum stability or maximum mobility? Now, the unsung hero of the modern LAN is this little box called a network switch. Think of it as the network's traffic cop. See, in the old days, when one computer needed something, it would basically shout its request to every single device on the network. It was noisy and inefficient. A switch is way smarter. It knows the unique address, the MAC address of every device plugged into it. So when your computer asks for a file, the switch sends that data only to you. It's a simple idea, but it's what keeps our modern LANs from getting hopelessly congested. These LANs can be set up in a few different patterns, or what we call topologies. Way back when, networks often used a bus, where every device just tapped into one long cable. It was simple, sure, but if that cable broke anywhere, the whole network went down. Ouch! Today, the star topology is king. Everything plugs into a central switch. It's much easier to manage, but you better believe that switch is a critical piece of hardware. There's also the ring design, where data travels in a circle, which gives you some built-in backup if one connection fails.
All right, so we've got our local office network humming along nicely. But what about a big company? What if you have offices in New York, London, and Tokyo? How do they talk to each other? Well, for that, we have to zoom out and look at the wide area network, the WAN.
So if the LAN is the building's private intercom, the WAN is like the global telephone system that connects all the different buildings. Its entire purpose is to link all those separate local LANs together, no matter how far apart they are. The WAN is what makes it possible for an employee in that New York office to open a file on a server in the London office like it was sitting right there on their own local network.
Now, building a WAN isn't a one-size-fits-all deal. You've got options. You could go for a lease line. This is like renting your very own private 3-lane highway between two offices. The performance is guaranteed and amazing, but boy is it expensive. A more common choice is MPLS, which is kind of like a premium shipping service for your data. It knows which packets are most important, like a video call, and puts them in the fast lane. But the most popular option today is a VPN, which creates a secure, encrypted private tunnel for your data right over the public internet. It's super cost-effective, but your performance depends on the internet's traffic that day.
And just like LANs, WANs have their own design patterns. A really common one is hub and spoke. All the smaller branch offices connect directly to the main headquarters. It's straightforward and keeps costs down. The alternative is a mesh network. Here, all the sites are connected to each other, creating multiple paths for data to travel. This is incredibly reliable. If one link goes down, data just finds another way.
But as you can guess, it's a lot more complex and expensive to set up.
Okay, we've connected our local office LANs together using a wide area network, or WAN. But what are those WAN connections actually made of? What are we building on top of? Well, let's peel back that final layer and look at the bedrock of all this, the telecom circuits, the real, physical highways of our digital world.
To understand these highways, you need to know about a huge shift in how data travels. The old way, used by phone companies, was called circuit switching. When you made a call, you got your own private, dedicated train track from you to the other person. Great for call quality, but totally inefficient if nobody was talking. The internet changed everything with packet switching. Your email, your video, your website, it all gets chopped up into tiny little packets. Each packet is like a car with an address, and it finds its own way through the network's traffic. It's brilliantly efficient and resilient, and it's the foundation of pretty much everything we do online.
The physical highways themselves have also gone through a massive upgrade. For decades, the workhorse was the T-carrier system, like the legendary T1 line, pushing data over good old-fashioned copper wires. But the real revolution came with optical carrier systems and fiber optics. By turning data into pulses of light and shooting them down glass threads, we blew the doors off what was possible in terms of speed. This is the technology that makes our high-definition, cloud-based world a reality.
And the scale we're talking about is just staggering. A single, high-end fiber optic line. And remember, there are bundles with hundreds of these running under our oceans, can carry 40 gigabits of data per second. To give you an idea, that's fast enough to download 1,000 HD movies in a minute. This is the heavy-duty backbone that carries our digital lives across countries and continents.
And this story of progress isn't just happening on a global scale. It's happening in the cable coming into your house. The standard for cable internet, called DOCSIS, has been getting better and better. It started by cleverly piggybacking internet signals on top of TV channels. Then, with version 3.0, it learned a trick called channel bonding, basically ganging multiple channels together to create one big data superhighway, which got us into gigabit speeds. And now, with DOCSIS 4.0 aiming for 10 gigabits, that humble coax cable is giving pure fiber a serious run for its money.
So, we've seen all the pieces, right? From the LAN switch in the wiring closet all the way to the global fiber optic backbone. But here's the thing. Just owning all the fancy parts isn't enough. How you assemble them, and this is crucial, how you document everything, is what separates a reliable, high-performing network from just a chaotic mess of wires.
I mean, why would a simple diagram or spreadsheet be so important? Well, imagine something breaks at 3 in the morning. With a clear map, you can fix it in 10 minutes. Without one, you could be down for hours. When you need to upgrade, you know exactly what you're working with. It also stops all that critical knowledge from being stuck in one person's head. You know, the so-called tribal knowledge that leaves when they do. And in a lot of industries, it's the only way to prove you're meeting your security and compliance rules.
And listen, this isn't just some nice-to-have idea, it's a full-on professional discipline. There are official industry standards like TIA 606 that spell out precisely how every cable, port, and panel should be labeled and documented. When you follow a standard like this, it means any qualified pro can walk in, look at your setup, and understand what's going on.
So, what does it all boil down to? A truly solid network is built on a few core ideas. You use things like logical segmentation to create digital walls that keep data from different departments safe and separate. You build in redundant physical paths so that one clumsy accident with a backhoe doesn't take your whole company offline. You even have to think about managing airflow to stop millions of dollars of equipment from melting down. But if I had to give you 2 golden rules, they'd be these. Always plan for at least 50% future growth and keep all your documentation in one place where everyone who needs it can find it.
So there you have it. From your local Wi-Fi connection to the mind-boggling fiber optic cables buried under the ocean, this is the invisible foundation holding up our modern world. And when you think about the future, with billions of new smart devices coming online, everything from cars to cities, the principles we've talked about of robust, scalable, and well-documented design, they're not just going to be important, they're going to be absolutely essential. The next great challenge for network architects is already knocking at the door.